Well, hello there, chemistry classes. This is Mrs. Sharp, and you have a brand new set of notes today, Unit 7, and we're going to start those notes today. This unit is on chemical reactions. Now, if you're like, wait a second, what happened to Unit 6? In the course of Miss Guntz taking over this semester, Unit 5 and Unit 6 kind of got sandwiched together, so we're going to skip right on over to Unit 7. And it makes us feel like we got farther, so that's good. So we are going to start with guiding question or learning target 7.1. We're going to talk about some chemical reactions, what changes, identify some stuff, learn how to write them, and talk about energy changes. So this learning target is right there at the top of your notes for you to look at, and we're going to go through all of those today. So first of all, what is a chemical reaction? What is its definition? And so a chemical reaction, by definition, is a chemical change. Now remember we talked about that at the beginning of the year. A chemical change where chemical bonds are first broken. So I'm going to highlight that. First they're broken, and then they are reformed. So old bonds are broken and new bonds are made. Now, don't be shy here, too. We can pause this as we go. You just got to ask nicely if you need some more time. But I'm going to keep on chucking here. So we've got a chemical change where bonds are broken and then bonds are reformed. So just as a reminder, too, back when we first talked about bonds, we said that anytime you want to break a bond, that's going to require energy. Okay. So remember, we call that endothermic. And then reforming is going to release energy. Anytime you make a bond, you're going to release energy. And that's exothermic. Okay, so in each and every chemical reaction, we have both of these processes going on. So it's going to take a little energy and it's going to release some energy. And it's just how those two compare if the overall reaction is going to give off energy or require energy. But both are happening at the same time. I'll show you an example of that later. So you always start with reactants on the left with an arrow to products on the right. So reactants are what we start with before the reaction takes place. Products are the new substances we make on the right as a result of making new bonds. So remember, the old bonds of the reactants are broken and new bonds are formed to make a brand new substance or substances. Those are called your products. Remember, a chemical change is a change in which a new substance is made with new properties. So that really makes sense. Anytime you have a chemical change, you should have a chemical reaction. And I'm not here today, so I guess I can't do that for you. Sorry. Just kidding, I wasn't really going to do it, but I've got some other really cool stuff to show you guys in this unit. So here are some 7 indicators of a chemical change. We talked about these earlier in the year, but just as a reminder, things to look for in a chemical reaction. 1, you may have a gas released, which you'd see by bubbles or fizzing. That means a gas is created. That's a good indicator that you have a chemical reaction. Now you got to be careful because you have bubbles when you just like boil water too, and that's not really a chemical reaction. So again, these are just indicators. So you may have a chemical change. If you have heat released, remember our term for that is exothermic. If it's exothermic overall, meaning you have more energy released than you need, then it might be a chemical change. It might be a chemical reaction. Heat absorbed, if it requires more energy than it gives off, it might feel cold, so heat is absorbed. That's how those cool packs work. Light is released, such as fire or glow stick, sparks. A precipitate formed, you guys know what those are after your 5.3 lab. You have precipitates formed. If you have one of those, you have a chemical reaction. And there's a picture. A change in odor, so not just an odor, but a significant change in odor, like there wasn't an odor to begin with, and there is one when you're done. That's an actual job, just so you guys know. is sniffing armpits of people to see the effectiveness of deodorant, and that change in odor is because of the reaction between bacteria in your armpits that produce an odor. Yep, that's a real thing. And changing color. So not just a color, but a change in color, going from white to yellow or something like that. So these are your 7 indicators, and you can look for those in a chemical reaction. So things that are not chemical changes or not chemical reactions, just as a reminder, those would be called physical changes, would be phase changes or state changes, melting, boiling, any change of state. Dissolving is not a chemical change, or changing of form, breaking, smashing. None of those are actual chemical reactions. All right, please remember, this is just a reminder, that both matter and energy are conserved in chemical reactions. That's the law of conservation of matter and the law of conservation of energy, which just means if you start with 50 grams, then you need to end up with your products having 50 grams. So it can look different, but you have to have the same amount of matter at the end of the reaction as you do at the beginning. Same thing with energy. So that's just a reminder. We talked about it a long time ago. So now let's talk some specifics. How do I write a chemical reaction? Well, we always start with the reactants and we end with the products, and there's an arrow in the middle. Anytime you see a plus sign, that is a separator. So a plus sign is going to separate reactants from each other or products from each other. And you read it as and. It's not plus, it's and. I know it's a plus in math class, but in chemistry we say and, or with, reacting with. Okay, so that is, it might be over here like 2 reactants. So you would separate those 2 reactants with that plus sign. The arrow means yields or produces or forms. And we'll say yields for right now. If you have a triangle over that arrow, that is going to show that heat is required for that reaction to go. So if you do not supply that reaction with heat, it might not happen. So a triangle over that shows that heat is required. If you have a kind of a zigzag or a lightning bolt over the arrow, that means that electricity or light is required for that reaction to happen. If you have a double-sided single arrow, so a single-sided arrow going both directions, that means that the reaction is reversible, which means it can go both forward and backward at the same time. It's kind of wild. If you see a parentheses lowercase s next to a reactant or a product, that means that that reactant or product is in the solid state at the temperature you're doing your reaction at. And then you've got an L for liquid and a G for gas. An arrow up means a gas is released. So on the product side, if what you are forming is a gas that's released, you can put an up arrow next to it instead of the G for gas. You can show a down arrow to show that a precipitate is formed on the product side instead of an S for solid. So if what you make is a precipitate, then you can put a down arrow next to it to show that it's a precipitate. And then finally, if you have in parentheses AQ, that means that it's neither solid nor liquid nor gas, but it's something that's aqueous, which means it's dissolved in water. So a lot of things actually do have to be dissolved in water first before they can react. So those things would be considered aqueous. So here's just some language and some symbols to help us write out a chemical reaction. Because if we don't have symbols and we don't have kind of a process for doing this, it can be a very long and tedious thing. So let me show you some examples of how this works. How do I write an equation, which we are going to from now on abbreviate EQN, equation, for a chemical reaction, which from now on we're going to abbreviate Rxn. So an equation for a chemical reaction. Now, you might be like, what's the difference? Well, a chemical reaction is what actually happens. An equation is the story to describe it. So think of the reaction as the game between Western and Lumen, the baseball game between Western and Lumen. The equation would be the story that goes in the paper afterwards to describe it. So, you have what's called a word equation. And so a word equation is always written first. The word equation is always written first. And it shows what reacts in words. So those reactants and those products are written out in words, which means it's very qualitative. You don't have any numbers. So it's a bit more general. And then you have what's known as the formula equation. And that shows the formulas of all the elements and compounds that are involved. So that's more quantitative. So that's a little more specific than a word equation. When you're writing a formula equation, this is really important. Watch out for your diatomic elements. Remember, those are elements that aren't in a compound that take the form X2. So they need a buddy. And you should have those marked on your periodic table, but just in case, your diatomic elements are H, O, N, F, Cl, Br, and I. There's 7 of them. And so if you have just hydrogen, you would never write hydrogen in an equation like this. No, that's bad. So if it's just hydrogen all by itself, it would be H2. If you have HCl, that's okay too, because he's got a buddy. But if it's just hydrogen, the element, not in a compound, he needs to be H2. So watch out for those. Those can really mess you up if you forget about them. Okay, so let's do some word equations and formula equations. This is going to be fun. Okay, so here is the chemical reaction. So here's the game. We put iron and oxygen and we heat them and we make a powder of iron 3 oxide. So I think you guys can tell that we're not going to really want to write out an entire sentence about a chemical reaction every time we want to describe it. So instead what we're going to do is write a word equation. Remember, and is our separator. Heated means we're going to put a triangle over our arrow. And when it says is formed, that means it must be a product. So let's try this. The word equation is going to look like this. Oh, there's my arrow. We're going to take iron. And again, remember to ask nicely if we need to pause this. So there's iron in words. Whoopsie. Iron in words form and oxygen in word form. And iron 3 oxide as my product. So right there's my skeleton. I've got the words of the reactants, iron and oxygen, and my product is iron 3 oxide. And now, I put some jewelry on here. So the first jewelry I put were all the states I could. And you might be like, whoa, Mrs. Sharp, you're so smart. How did you know iron was a solid? Well, iron is a solid at room temperature, and because that kind of goes without saying. And oxygen is a gas at room temperature. And iron 3 oxide is a solid because it says a powder, which would be a solid. So I went ahead and added all of those that I could on there. Now you might not always know every state, but if you know the state, then you should definitely put it on there. And then finally, like I said, we said it was heated. And so over my yield, I put the triangle. So there's my word equation. Now let's try your formula equation. Formula equation. All right, same information, just quantitative, so meaning I have formulas. So my iron reactant, iron is an element and it's not diatomic, so Fe is fine. Then we've got our separator, oh, and it's still a solid. Then we have and, iron and oxygen. Okay, now oxygen is diatomic, so it's a gas. When I write it, I can't write just O, I have to write O2. And it's a gas. And it still requires heat like it did before, so we're keeping that part. Nothing's changed there. And then the iron 3 oxide, this one's tricky. Look at the formula for iron 3 oxide. Fe2O3. So notice we didn't just write FeO. And that's because this is an ionic compound. So iron 3 oxide would look like this. Fe plus 3. Oxide would be O minus 2. Remember that plus 3 is from that Roman numeral there. So if I were to balance this, I would need 2 Fe's and 3 O's. And so that's how we get that formula. So just be really careful. Just because it says iron and oxygen, you can't just write FeO. We have to write the formula just like we've been learning to. So that's my formula equation. Now, one thing that you guys may do is look at this and say, oh my gosh, is only 1 Fe over here and 2 over there. that's not balanced. And you'd be perfectly right. It would look like we created an extra iron. So we would go back and balance this. And we're going to talk about this a lot more later, so please don't freak out right now. But if I was going to balance this, I'd want to put 2 here for 2 irons. And then our oxygens would have 2 and 3, so that would make things weird. So I guess what I would need to do is make this a 3, so I would have 6 oxygens. And then I'd have to put a 2 here to make this 6 oxygens, but that would also make me have 4 Fe's. So I need to go back and make this a 4. Now if you're like, oh my gosh, I don't like balancing equations, I struggled with it when we learned about it last year or 9th grade or whatever, do not worry about that right now. I will teach you how to do that. And I have lots of good strategies and tricks for doing that. But we're not going to worry about balancing it, but if you were thinking that, then you're right. We would need to go back and balance it. So there you have your word equation and your formula equation. Now let's talk about energy. It doesn't matter what kind of reaction you're talking about, every single one is accompanied by some change in energy. So that means all reactions are either endothermic or exothermic, one or the other. If they require energy, a process or a reaction that requires energy, that reaction is going to be called endothermic. And if it releases energy, it's going to be exothermic. And remember that first they break bonds, which is endo, and then they make bonds, which is exo. So it just depends on which one is more. Like, for example, if I wanted to start a cupcake business for school, and I put $20 in, but I sold enough cupcakes to make $100, then I would net $80. So we might say that's exothermic. But if I put in $20 and I only made $2, then I would be out $18. So that would be an endothermic process. So it just depends on which one is bigger or which one takes more energy. If you're taking more energy to break the bonds or if you're releasing more energy when you make them. So let's take a little bit closer look at this. The overall change in energy in a reaction is symbolized by the symbol DH. Now this is funny because when I put this into my PowerPoint, the formatting got messed up. So this isn't even really the symbol for this. So the symbol is not that. The overall change in energy in a reaction is symbolized by the symbol delta H. Okay, so delta H shows the overall change in energy. So when we look at the overall change in energy, if it's positive or negative, it can tell us if that process is endothermic or exothermic, and that symbol is delta H, change in energy. I don't know why they chose the letter H, but they sure did. Okay, so if that value is positive, okay, so here's an example of an exothermic reaction. And that is between magnesium, and we should add, this is the formula equation, so we should add some jewelry in here. Magnesium, which would be a solid, and 2 HCl, which is actually hydrochloric acid, which is a gas dissolved in water, so it would get an AQ. And then magnesium chloride is an ionic compound that dissolves in water, so it would get an AQ. And then hydrogen is a gas, so you could write a little G there in parentheses, or since it's a product, you can write a little arrow going up next to it like that, which means it's released, it's coming out. Whoops. So there we go. This is an example of an exothermic reaction. You guys are actually going to do this reaction, and since it's exothermic, that means we can expect for it to release energy. So this one releases a lot of heat as it happens. So not only does it release hydrogen gas, but it releases a lot of heat. So we have a graph here of potential energy. And what we're going to do is we are going to draw our reactants here at some amount of energy. And this should look familiar to you guys. We've done this before. And then we are going to show all of those elements separate. So the magnesium, the hydrogen, and the chlorine. So it's like we broke all those bonds. And remember, that always requires energy to do that. So energy is always required to break those old bonds. And then when you're done, our products have very low energy. They're very stable. And so energy is always released, that's in purple, to make new bonds. And our purple arrow is bigger than our green arrow. So that means that this reaction overall is exothermic, because overall our delta H is negative, meaning the energy went down overall. So that's just this big purple arrow, the difference between the reactants and the products. So overall, so think about my cupcake example. If I started with $20 and I made $100, then overall I benefited $80. So in this case, it lost energy, and so we don't even consider this stuff up here. That doesn't factor in. It's just this overall change in energy is down. So if ever delta H is negative, that always means the reaction is exothermic, because the energy decreases, which means energy is released. So now let's look at an endothermic. Oh, by the way, this is called a thermochemical equation. Remember, anytime you see this weird D, it's supposed to be a triangle. So that should be triangle H, and that should be triangle H. The thermochemical equation is just the formula equation here. That's the formula equation. And then you have some space, and then you have the value of your delta H. And see how it's negative? That means it's exothermic. Now that 437, you'd have to, somebody would have to give that to you, or you'd look it up somewhere, but kilojoules. So 437 kilojoules are released during this reaction. Whoa. Okay, so now let's look at an endothermic reaction. Here we have baking soda, and baking soda is decomposing into sodium carbonate, water, and carbon dioxide. So let's add our jewelry onto this as well. Baking soda is a solid at room temperature, and sodium carbonate is 2. You might not have known that. Water, you guys know, is a liquid, which I always do a cursive L because my L's look like I's. And then carbon dioxide is a gas, as you know. So we can do our little up arrow guy, or you could do your parentheses G for gas if you prefer. It's up to you. So in this reaction, we have an endothermic reaction. So we have kind of the opposite situation going on. So again, we're going to show our reactant first, NaHCO3. There's our reactant. And then if we break that into pieces, we would get Na, H2, C, and O2. So those are all the elements. So if we broke it into its elements, remember, no matter what, it always takes energy to break bonds. So that's going to require energy. And then when we put them back together, we make new bonds. We're always going to release energy when we do that. But now look at what we got going on. If we look at overall what happened, the energy went up. And so if energy goes up, then that means delta H is positive, which means overall you're going to require energy to do this. It's endothermic. So if the energy goes up overall, it's going to be an endothermic reaction. So at this time, our green arrow definitely outweighed our purple arrow back down. So look at our thermochemical equation and how it differs. So again, you've got your formula equation here. And then our delta H, after our little space there, delta H is positive 35 kilojoules. So again, I don't really care about this number, is not important to me. What's important is that you know that if it's positive, it's endothermic. So it's going up in energy 35 kilojoules. Okay, so that was a lot of information. We're going to stop there. Just a reminder, you have a big old LTA tomorrow, 5.5% comp, empirical formulas, molecular formulas, hydrates. Whew! It's going to be humongous. So make sure you finish off those practice problems in the time you have left. Make sure you finish your lab in the time you have left. Make sure you check out the Can You on Edmodo and email me if you have any questions. All right, that's it for Mrs. Sharp. Have an awesome day, and I'll see you tomorrow.